So imagine for a moment you're on a boat, and this boat is out to sea, right? You're in the middle of the ocean. Now imagine that this boat is starting to sink. So you are in a situation where you need help and you need it quick. Now you know that there are probably other ships in the vicinity, and they're going to be your quickest source of help. They're going to be able to render aid quicker than any dedicated rescue team will. Now, you also know that these boats carry radios, and they're required to monitor the emergency frequencies. So you rush over to your frequency modulated VHF marine radio, and you place a distress call. You call Mayday, 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 and then you listen. And you don't hear anything. You place another distress call, and you listen, you don't hear anything, and this goes on. So how could modulation type have affected you in this life or death situation? My name's Jack. I'm an aerospace engineer. I've been involved with amateur radio for the better part of 20 years, designing and building various radio circuits. I've researched this topic, and I'd like to share some of the information with you. And today what we're going to be talking about specifically is a form of modulation called single sideband, and a specific flavor of that called single sideband suppressed carrier. And I want to talk about how modulation type, and specifically this modulation type, affects things like band crowding, radio range, as well as signal to noise ratio. So radio voice communication since its inception has had a variety of problems. And these are affected to a certain degree by your modulation type. So one of the biggest problems, especially as radio began to be more popular, was band crowding, right? Too many frequencies in a given range. So the radio frequency spectrum only has so much range to it, right? So much bandwidth. And each band within that radio frequency range also has a limited amount of space. And the number of stations that can fit within a given band is a function of bandwidth, right? The wider the bandwidth, the fewer the number of stations that can operate on a given band at any one time. Narrower bandwidth stations, you can fit more of them on a given band. Common sense, right? Another problem that's plagued radio is low range. Now, there are many other causes other than modulation type that affects range. For instance, the type of antenna that you use, how high that antenna is, what frequencies you're operating on, the amount of transmit power that you're using, the type of terrain that the signal is having to traverse over. You know, is it flat terrain? Are you trying to go over mountains? Even the weather can affect your range and how far that signal is actually going to go and how far it's going to be usable till. One of the chief considerations when it comes to range is something called spectral power density, and this is affected by modulation. Now, spectral power density is a function of bandwidth. So if you have high bandwidth, that power is spread over a broader range of frequencies, so it's less concentrated, and it's going to lower the spectral power density, and it's going to lower the range. In contrast, lower bandwidth signals tend to travel farther because they have high spectral power density. The power is much more concentrated within the frequency spectrum. Also, whether or not this signal has a carrier. So a carrier acts as a reference point for demodulating the voice information part of the signal, but the carrier itself actually doesn't transmit any information. And so it has a tendency to waste power and lower your spectral power density, and that can reduce the range. Another problem is signal to noise ratio. So high signal to noise ratio is a good thing. It makes the signal more detectable and less likely to be masked by the noise, what's called the noise floor. High bandwidth, on the other hand, increases the amount of noise that the receiver is going to receive. It's not going to filter out, and it lowers, meaning it has a negative effect on signal to noise ratio. So clearly there are some problems with radio voice communication. You know, it's a small miracle that it happens at all, considering the tiny fraction of original transmit power that actually makes it to the receiving antenna. But let's take a look at how modulation can affect some of these problems. So the biggest thing modulation can do is it can reduce the bandwidth. So this is going to have the most effect in mitigating some of these problems. So according to Stanford's Amateur Radio Club, the bandwidth of a typical AM broadcast station, a voice station, is going to be about 6 kilohertz, give or take. Now if you're using frequency modulation, FM, that jumps up to 15 kilohertz. It can be as low as 5, but typically 10 to 15 is where you're going to see it at. So that's a pretty wide bandwidth signal. Now single sideband, on the other, uses about 3 kilohertz. It can go as low as 2.8, 2.4, but around 3 kilohertz. So it's much narrower than these standard AM and FM types of modulation. So how is lowering bandwidth going to help some of these problems? Well, band crowding, for instance. Now, according to Gil McElroy of the American Radio Relay League, single sideband can fit more channels into a given frequency range or a given band. And there was a study done by Morrow, Mack, Nichols, and Leonard that showed that using single sideband, you could fit 4 times as many stations into a given band versus using an FM voice type of modulation. So what about range? So McElroy noted that single sideband doesn't waste any power transmitting a second sideband, because that second sideband contains the same information as the first. It's redundant information, so it's a waste of power. And AM, standard AM, wastes at least 50% of its transmit power sending out that carrier frequency that acts as the reference point for voice demodulation. That's the best case scenario. Oftentimes it's more than 50%. And single sideband transmits no carrier. So no carrier means more power can be devoted to that one sideband. 100% of the power can be devoted to that one sideband that contains all the voice information. And this greatly increases the spectral power density and increases the range. Morrow's team also found that a usable single sideband signal is going to need about 20 decibels less power than an equivalently usable or intelligible FM signal. So that's about a 100-fold difference. Morrow's team also found that single sideband transmissions will tend to go much farther than an equivalently powered AM or FM signal. So what about signal to noise ratio? Well, Chris Malinsky of Radio Hobbyists notes the first way that modulation can affect this. Now, single sideband's narrow bandwidth will increase the spectral power density. And also its lack of a carrier means more power can be devoted to that one sideband, also increasing the spectral power density. So this increases the signal portion of that signal to noise ratio. The second way, Smolinski says, is through a narrowing of the passband, right? So what the receiver is going to do is it's going to filter out more of the noise and allow less of it to come in. So that reduces the denominator. So the overall effect is that you're going to get a much higher signal to noise ratio with a single sideband transmission. So this means that the signal is going to be intelligible for a much longer time as it gets weaker and farther away from the transmitting station than an equivalent AM or FM signal. So what are the key takeaways from this? Well, number one is that bandwidth matters. A reduction in bandwidth is going to mean that more stations can fit on a given band without interfering with each other. Also, a reduction in bandwidth is going to increase spectral power density, and this is going to increase range and also improve signal to noise ratio. Now, there's always going to be noise, but that reduction in bandwidth is what really improves the signal to noise ratio. Also, carrier signals. Now, for broadcast radio, carrier signals are fine because broadcast radio stations have an abundance of power. They're not worried about power. They don't need to go particularly long distances. It allows for cheap receivers. But when every watt needs to be dedicated to actually transmitting the information, the voice part of the signal, then single sideband is definitely going to come out on top as far as efficiency, because single sideband doesn't broadcast that carrier signal, so there's no waste of power. Now, every modulation type is going to have its strengths and weaknesses. But single sideband's combination of low bandwidth and no carrier signal has meant that it has had very good performance, and it's been used for decades to solve some of these common issues with radio transmission. And because of this high performance, it's likely going to be in use for decades to come. Thank you for listening to my talk today.